Hello and welcome to the history of the atomic model. The atomic model originated in ancient Greece over 2,000 years ago when Democritus, a Greek philosopher, asked this question: if we divide something in half over and over again, when will we get to the point where we can no longer divide it? He proposed that matter was not infinitely divisible and was made up of tiny particles called atomos, which means indivisible in Greek. He believed that atoms could neither be created nor destroyed or further divided. He also believed that these particles moved through empty space and that different atoms of different elements varied in shape and size. However, he was shut down by many other philosophers of the time when they asked him, what holds these particles together? Another famous philosopher from the Greek era that seemed to want to shut down Democritus' ideas was Aristotle. Aristotle believed that atomos couldn't exist and couldn't move through empty space because he didn't believe that empty space was possible. Aristotle favored the idea that matter was made of the natural elements: earth, fire, wind, and water. His ideas were more favorable because he was the more respected philosopher. After the Greeks, nobody really talked about atoms and the atomic theory for 2,000 years until John Dalton brought back some of Democritus' ideas in the 18th century. Before we talk about John Dalton, I would like to bring up two other scientists who also inspired John Dalton: Antoine Lavoisier and Joseph Proust. Lavoisier discovered the law of conservation of mass, which states that matter can neither be created nor destroyed. Joseph Proust discovered the law of definite proportions, which states that a given chemical compound always contains its component elements in a fixed ratio. John Dalton came up with his own atomic model 2,000 years later after Democritus did, where he concluded that all matter is made of atoms. Like Democritus, he said that all atoms are indivisible and indestructible. He said that all atoms of a given element are identical in mass and properties. He also came up with the idea of compounds and how they are formed by a combination of two or more different kinds of elements. His model depicts atoms as circular, which is different from Democritus' idea that different atoms of different elements have different shapes. J.J. Thomson is the next chemist to come into play. He experimented with cathode rays and he discovered the electron, a negatively charged subatomic particle. His new atomic model was called the plum pudding model and shows a circular atom that maintains an evenly distributed positive charge with negatively charged electrons scattered inside of it. Now, Ernest Rutherford, a student of his, found flaws in J.J. Thomson's model. He decided to test out the properties of atoms further by using the gold foil experiment. In this experiment, he tested to see if the positively charged alpha particles would go through a thin layer of gold foil easily. When the particles bounced back, that meant that the positive charge of the atoms is not evenly distributed, but actually have a very small positive nucleus. His atomic model was called the nuclear model of the atom. Now, there are other discoveries that help with the development of the atomic model, such as the studies on properties of light and energy. Max Planck wanted to know why, when something was heated, it didn't show the full range of colors. Rather, it just showed a glowing red, orange, or yellow. He concluded that matter can gain or lose energy in only small specific amounts, called quanta, and that a quantum is the minimum amount of energy that can be gained or lost by an atom. Einstein studied the photoelectric effect and light's dual nature. The photoelectric effect is when photoelectrons are emitted from a metal surface when light of a certain frequency shines on the surface. So for an electron to be emitted from a surface of the metal, what matters is the light's intensity, not the duration of shine. Because no matter how long you shine a light on a metal, if the intensity or frequency isn't powerful enough, the energy will not be able to pass the threshold value. Einstein also concluded that light moves in waves, but also has particle-like features, which are photons. Niels Bohr built on Planck's and Einstein's ideas of quantized energy. He proposed that the hydrogen atom has energy states. When energy, such as photons, bounce off electrons, they jump to higher energy states, but move to lower energy states when they lose energy. This is what is called the planetary model of the atom. Now, Einstein may have concluded that light has dual nature, wave-like and particle-like. Waves can have particle-like behavior, but de Broglie reverse engineered that thought and concluded that particles can also have wave-like characteristics. Now, many of these scientists Rutherford, Bohr, de Broglie, Planck have been trying to unravel the mysteries of the atom. But Werner Heisenberg discovered something that would change how they saw the atom forever. Everyone wanted to know the position and velocity of electrons, but Heisenberg said that it was impossible to see that at the same time. The Heisenberg uncertainty principle states that it is impossible to know precisely both the velocity and position of a particle at the same time. Think of electrons. If scientists wanted to see electrons, they would need light. But photons are about the same size as electrons. So if you were to shine light on the electron would receive energy and move immediately. Think about a rat in the dark sewer. You can hear the rat, but you can't see it. But if you shine your flashlight on the rat, it'll run away immediately. This brings us to our last scientist, Erwin Schrödinger. Schrödinger used quantum mechanics and the discoveries of all the scientists before him to create the quantum mechanical model of the atom. This model is similar to Bohr's, but makes no attempt to describe the electron's path around the nucleus. He is also very famous for an experiment called Schrödinger's cat experiment. This is an attempt to showcase the properties of quantum mechanics and how very small particles don't behave like the world as we see it. And that's it! Those are all the atomic models and the most important scientists who contributed to it. Thanks for watching!
Yeah.